All right, good morning. My name is Alan McInnes. I'm a solutions architect here at AWS. I work in our big data space, primarily focusing on streaming data, helping a lot of customers do what we're about to talk about today, which is moving from batch to streaming. So in my role, I traditionally talk to customers about streaming data, things like Kinesis in our space, which we're going to talk about a bit. Talk a lot about things like Kafka as well to our customers. Today we're going to focus on, though, kind of just in some general terms, to some extent, how to move from batch to streaming. We have with me, sitting off to the side, but he'll join us about halfway through, Brandon Smith. And he's going to talk to you specifically about how his team in Amazon Flex did this exact thing. So kind of the first half, I'll cover a number of things like the real-time streaming data overview, just so we're all on the same page, get some information to you about just what is batch, what is streaming. And then we'll jump over to Brandon, who will cover a lot more detail about what they did. So hopefully you can learn something from what other teams within Amazon have done to make this transition. So we'll start by sort of setting a little bit of context. This probably isn't very new to most of you, but what is batch processing? Maybe a show of hands. Who here has either worked on or is already familiar with a batch process in your organization? Right? Been around for years. So what does the community say it is? Wikipedia, execution of a series of jobs in a program on a computer without manual intervention. That's a lot of words. What's funny is the definition of batch actually goes way back when we used to use punch cards to program computers. So we had these cards, right, with all the little cutouts that indicated the code, and they were fed to the machines in batch, right? They were provided in small batches to the machines to program them. So that's kind of where the term batch started. But what does it mean in the big data space, or even in just the data space? It's typically data collected over a period of time, processed and analyzed on a relatively regular schedule. Could be every hour, could be every day, could be weekly, could be monthly. But it's a well-known schedule doing something with that data. And then typically you combine several of these together to obtain your final result. So like I said, you might have an hourly job, and then at night you might roll up some of these hourly aggregations into another value, put that into another table. So typically batch processing is doing this continuously, and it's using multiple batch jobs to get your final result. A great example of batch, which I think you'll all be familiar with, would be something like your credit card statement, right? They obviously send you a bill once a month, and how do they do that? It's a batch job, most likely. They probably have some real-time components in there, which we'll discuss, but in general, this statement that you receive once a month, it's a batch job, right? It's running on a regular schedule, collecting a bunch of information, doing some aggregation, and giving you the result. So that's a high-level view of batch. So when we get to talk about streaming, we think about data that's produced continuously. Now, what's interesting here is that even in a batch world, the data that's being batched is, in most cases, still being produced continuously, right? Whether the data is coming off of a mobile app or clickstream data from a website, application logs, things like metering, IoT sensors, all of these things are being created continuously so that we can kind of learn more about what's going on in our business right now. So that's sort of how we start talking about going from batch, where we're taking data and doing things with it on an hour or daily basis. But that data was created continuously. So now we look at the data and we think, well, this is being created continuously. How can I take advantage of that? Going back to that credit card example again, imagine you're using your card, you're all in Las Vegas, you're probably not from Las Vegas. Maybe some of you swiped your card here at the casino to take some cash out. Maybe you swiped it at a restaurant and you got an alert from your credit card company saying, hey, I noticed a weird transaction. You were in New York yesterday, now you're in Las Vegas. Reply 1 to this text if that's you. So fraud detection in the credit card space, right? That's a great example of a real-time use case of how they're analyzing real-time data to make some intelligent decisions that help you as their customer. So that starts to helps us to think about kind of the value of our data and the diminishing value of data over time. So we like to think about recent data being very valuable, if you can do something with it. So that fraud detection is a great example. There's a great paper from Forrester Research called Perishable Insights. That's where this chart comes from. But it talks about you can make time-critical decisions with data that's being created right now. And then as time goes on, the older data becomes less valuable, but its importance can be increased if you can combine that old data with the new data that's being created right now. So imagine I'm generating real-time data from, let's use a clickstream example. I've got a website. I've got people clicking on it, viewing web pages on my website. If I can combine an aggregate value of how many users are looking at this particular item on my website in the last hour, and then compare that with the same item that the number of customers viewed last week, last month, last year, I get some insights into how my business is doing, maybe with a promotion that I ran on that particular item, right? If I can tell that I've got a lot more visits to this particular web page in the last hour than I did in the same hour yesterday, and I ran a promotion last night or an email campaign, great, I'm getting some success. I'm seeing that in real time, I'm seeing that my campaign has been successful. So recent data is very valuable if you can act upon it. So how do I process this real-time streaming data? Kind of a 5-phase process. Now, most customers that I work, they don't have to do all 5 of these things when you're talking about processing streams. But in general, of course, you collect the data. In most cases, you transform it in some way. And I'm going to get into more detail about this shortly. Some amount of analysis, and then you react and persist. So these are kind of the 5 steps that is very common, but a lot of times some people just collect, transform, and persist. Maybe you don't want to analyze it right there on the spot. Maybe you don't have to react to it. Maybe you just want to persist it so that you can do some analysis later. That's all fine. It's still part of the streaming data kind of workflow. Key requirements to building a streaming data system, and these are pretty typical kind of these aren't necessarily specific to like the Amazon Kinesis suite of products, but I'll talk briefly about what Kinesis can provide in these 6 areas. So a streaming data system needs to be durable, right? When I write data to it, the data needs to be persistent, and I need to be confident that my messages that I'm streaming to the system are stored in a durable manner. It needs to be continuous. So as data is flowing through the system, I need to be able to process it in close to real time if that's my requirement. So a continuously processing system is very important in the real-time space. It needs to be fast. Now, the typical definition that people, when I talk to customers, like, what's real-time to you? A lot of times they're like, well, real-time doesn't have to mean sub-second. To me, like, if I get an answer in a minute, that's great. That's real-time enough for my business. So fast is a little bit contextual, right? It depends on what is your definition of fast. But in most cases, sub-second in our space, we consider that pretty fast. And so the system needs to be able to support your requirements in that regard. It needs to be correct. So there are semantics in real-time processing like at least once processing, only once processing. So these are important to make sure that you maybe don't introduce duplicates into a downstream system. So your system needs to be able to support that. It needs to be reactive. So if you're trying to do something with that real-time data, perhaps you want to alert an operator in your organization that there's an anomaly on the stream, right? You need to have the ability to do that. It needs to be reliable. So if there's issues in the system, it needs to fail quickly, fail fast, in other words, so that it comes back without having an impact on your system. So it needs to be a very reliable platform. And so with that, we'll talk about a few of the systems that we have at AWS that enable those bullet points that I just discussed. We have 3 products in the Kinesis space, and these are all part of our streaming data products. Kinesis Streams, Kinesis Firehose, and Kinesis Analytics. Now, quick show of hands, how many folks are already using one or some of these today in your environment? Awesome, that's a pretty good show of hands. So then I won't spend a ton of time. I know most interesting is kind of Brandon's talk on how they've done this, so I won't spend a whole lot of time here, but we will quickly cover what they do so that if you're not familiar with it, you can kind of get a good idea of how they might help you. So Kinesis Streams, this was deployed about 5 years ago. We call it here, one of these bullet points says for technical developers. The reason we say that generally is because when you're producing data to a stream, you typically have to write code to produce the data, and you also have to write code to consume the data. So the streaming component, the buffer in the middle, is a managed service. But you're generally writing some code on both ends to put the data in there and to get the data off. Now, Kinesis Firehose is one level higher in the, it abstracts some of the consumer side away from you. It's like a managed consumer on top of a stream. So while you still may have to write code to produce data to Firehose, Firehose will have a managed consumer that will take data off of the stream and persist it somewhere that you configure without you having to touch any code. So I'll get into more details on Firehose in a moment. And then analytics. So now that we have our data streaming through either Kinesis Streams or Kinesis Firehose, how can I get some insights into that data? And that's what Kinesis Analytics provides. It gives you the ability to see into your data using standard SQL and do things like filtering or aggregation on your streaming data. And it can use data that's either in Streams or Firehose to do that. So Streams gives you the ability to reliably ingest and store streaming data at low cost. You build your own custom real-time applications. So in this picture, you see there's kind of 4 consumers. Now there's a few different ways that you can consume data off of a Kinesis stream. We have Kinesis Analytics on the top, which I'll talk about, and as I just mentioned. Very common is something like Spark running on EMR. So if you are a Spark shop, you already have Spark developers, then if you aren't into streaming yet, then if you implement something like a Kinesis Streams, you can implement Spark as your consumer on top of a Kinesis stream. Probably the most common thing that we see, we have a library ourselves called the KCL, the Kinesis Client Library, which is a consumer library for Kinesis Streams. And that would be the third point here, the custom code on EC2. It's probably the most popular stream processing library that runs on AWS today. It's a very simple library. It abstracts a lot of the complexities to stream processing. A very popular choice for doing stream consumption. And then the fourth one is the simplest, and it's gaining a lot of traction, is to use Lambda. So quick show of hands, AWS Lambda. How many folks here are pretty familiar with that? Good show of hands, awesome. Yeah, Lambda is great. It's our serverless compute service. You just write your function. You write like the business logic of what should happen to the data that's on the stream. And then you make the relationship just through a configuration. You say, this function is going to be the subscriber to this stream. And then the function just automatically gets invoked and your business logic is applied. So it's a very simple way to do stream processing. And that's becoming very, very popular because of its simplicity. So Firehose, like I said a moment ago, the nice thing about Firehose is the managed consumer. So if I go back one, all of these 4 things that you see here, analytics, EMR, custom code in EC2 or Lambda, you have to do some amount of coding, right? Whether it's SQL or the code in Lambda or your own custom code in Spark or the KCL application, it's your coding. Here, you're just configuring where does my data go. You say, I'm streaming my data into Firehose. I just want to land it in S3. That's all I want to do. I want to take my streaming data and I want to dump it into S3 so that I can run some other processes on it later. Or I want to put it into Redshift. If you're already a Redshift customer or our data warehouse platform and you just want to put your data in there, very simple. Just configure Firehose. Firehose will automatically manage how that data gets delivered into these destinations. And the destinations are S3, Redshift, and Elasticsearch service. It's just configuration on your end, no custom code required. There is some coding you can do as a part of Firehose to do data transformation kind of on the fly, and I'm going to talk about that in more detail, which is really cool. But in general, Firehose just gives you that one layer of abstraction, so you don't have to write any custom code to get your data, streaming data into these destinations. And then analytics. So I think I discussed it probably in as much detail as we need to, but basically, you have your data in either Firehose or Streams. You want to do something with it. You want to say, how many times has this event occurred in the past 5 minutes, right? You write a very simple SQL statement that does a select count from, and there's some lower level stuff that we're not going to get into in this talk about how your data gets mapped into a schema, because yes, it's SQL, therefore it needs a schema. Kinesis Analytics will infer a schema automatically based on what it sees in the data. That gives you the capability now to write SQL against that schema. But things like select count from, select from where, like applying filters, these are all very standard SQL statements that I'm sure you're all very familiar with. You can write those, have SQL Analytics apply those in real time against your stream, and give you real-time results. So doing streaming analysis, what are some of the benefits of it? The first one is, and this is by far and away kind of the biggest benefit that we see, is getting the immediate results. So if we think about when I was talking about Kinesis Analytics and doing something like select count star from my stream, that's a pretty common batch job, right? A lot of times you're doing hourly roll-ups. So let's say in your data warehouse or in your batch backend, you're saying every hour I run this job to do a roll-up. So this is some batch job that's running on the back end, giving you a count, moving that data into a different table in your data warehouse. Wouldn't it be great if you didn't have to run that batch job? Just have those aggregations being done on the fly. So my data is being streamed. I'm running a job that's looking at the streaming data in real time, doing the count in real time to say how many times has this thing happened over this past hour. And then the output is that one value, right? The aggregate value that you then save into your database. So now you don't need that batch job anymore to do those hourly aggregations. You have perhaps 24 rows that you create, one for every hour in real time in your database, and each row just contains the hourly roll-up right there on the fly. So it's pretty powerful. You don't have to wait until tonight to get the hourly results, right? They're done right there as soon as that hour window closes. So getting those immediate results is one of the most powerful things you can do with kind of a streaming data analysis system. Doing streaming filtering is also very powerful. So a lot of times, somewhere in your ETL process on the back end, you do a certain amount of filtering. You probably say, oh, this data right here, I don't really need it in this job. Yes, it's in my source data, it's in this database, but I'm just going to run part of my SQL statement is in my batch job and get rid of this data. So just get rid of it in real time, right? As the data comes in, if it's a data type that I'm not interested in for my analysis, just filter it out as part of your query, right? Your real-time query just says where this is, where these values are within this set that you care about. Therefore, all the other data that's not useful for that particular job, it just goes away. Don't need it for that. Things like anomaly detection. So I talked about the credit card use case. That is one of the great benefits of getting immediate results from your streaming data is was my credit card used in a place where it shouldn't have been? Kind of in a more realistic sense, we have a lot of customers who do things like collecting all of their application logs across all of their servers in their fleet. That could be hundreds, dozens, or hundreds of servers. They can stream all those logs through a Kinesis stream or Kinesis Firehose, and they analyze it with something like Kinesis Analytics, and they look for anomalies. So in an Apache Access, I've got a customer who looks at Apache Access logs, and they do a count of how many 500 response codes were returned by all of their systems in aggregate. And when it goes beyond a threshold that they've set, they're like, something's messed up here, and they alert their operators to go take a look at it. So very great way to do anomaly detection is streaming the data in real time and building some analysis on it right there as soon as it's generated. In many cases, it can reduce your complexity. Depends on the complexity, of course, of your batch jobs. But if you have a lot of different jobs doing things kind of either in order or out of order on an hourly or daily basis, like I was mentioning earlier, if you can do some of that in real time, you can remove a lot of those batch jobs off the back end. In most cases, I would say we're not suggesting that your batch jobs go away entirely. This is just likely going to simplify your batch processes because you're doing a lot of the roll-ups in real time. And it's fully managed. So all the Kinesis services that we just discussed are fully managed. There's no servers that you need to manage to make this work. Very, very simple. Just a lot of configuration, and that's it. No servers, and potentially very little code if you're using something like Firehose. And it's very scalable. So it enables parallel processing. We didn't get into the details of streams and how it scales, but things like Kinesis Streams and Kinesis Firehose, as your data ingestion rate increases, there's really very little you have to do to support that. In the Kinesis Streams case, you might just have to go add a few shards. In the Firehose case, there's nothing. It automatically will recognize that the rate at which you're adding records to the stream maybe has reached a threshold, and under the covers, Firehose will increase capacity. So there's very little you have to do to manage a kind of ever-increasing ingestion rate. And horizontally scale, so that's kind of the point I just made. You can easily scale wide to support more data. So before Brandon comes up, we'll talk about a few best practices. I think this will help put a lot of these things together. The first thing, and this doesn't always apply to just, this doesn't just apply to streaming, but if you're thinking of moving from a batch to a streaming solution, don't boil the ocean. Don't try and do it all at once, right? There's some techniques that you can take that will make it much simpler. So we take a look at this picture here. Pretty typical example. We've got something producing data. It's an application, writing to some app databases. I have an example of just a simple ETL job here that's taking some data and maybe dumping it into a data warehouse. And then maybe there's some other ETL jobs that are running against the data in the data warehouse. Really simple example, right? So begin by streaming your data in parallel to your existing batch process. There's very low risk and very little cost associated with just streaming the data in parallel to your batch. So let your batch run. Your business probably depends on it. So your first step could be, OK, I'm going to put a producer on my application that's going to take their log records and just forward them off to Kinesis. And then I'll just drop those data into S3, and I can do something with it later, right? Very simple first step. And then add in your streaming analysis over time, right? So as I do using Amazon Kinesis to do things like doing the aggregations in real time, it can forward the aggregate values straight to the database. And I can, over time, I think my slide built out there. Yeah, so you can see, right, over time, certain components of my system will go away as I slowly add more capabilities to my streaming data system. So the point of this one is, do it incrementally. Don't worry about going from batch to streaming all in one shot. Pick the pieces that make the most sense for your business and do it in parallel. Another best practice is performing ITL rather than ETL. So what do we mean by ITL? Ingest, transform, and load, as opposed to extract, transform, and load. So ETL, of course, means typically we extract data from another database, another data source somewhere else, right? We have probably relational databases scattered throughout my architecture, and ETL jobs are running to take data out of one, do some combination, and put it into another. Well, if I talk about ingest, transform, and load, that means I'm taking the data as it's created, I'm ingesting it, and then I'm transforming it and loading it into my downstream systems. So how can we do that? So doing the transformations in near real time rather than a scheduled job. So a lot of times your data that's coming in as input might be in one format, which might not be quite the same format that you need in your downstream system. So a very simple example, perhaps your downstream system is Elasticsearch, as a very simple example. Elasticsearch wants you to upload JSON documents into the indices. What if your data that's being generated is CSV or some unstructured text or some other delimited type of text that is, your application produces? Well, if you can transform that in real time, you don't need a back-end job to do it, right? So transform it in real time using something like Firehose and Lambda. So Firehose has direct integration with Lambda that allows you to write a very simple Lambda function that will take the raw data in Firehose and apply your business logic. And in this case, it might be converting from something unstructured to JSON. And then it'll return that data back to the Firehose system, which will then persist the JSON into something like Elasticsearch. You can also enrich the data on the fly. A very common back-end batch process is enriching this data. I have data over here, which might be keyed by something like a customer ID. And perhaps in my destination table, I want to include the customer name as a part of the record that I dump into this other table. Well, if I can, and you might have a back-end job that does that as a part of the ETL job. It enriches the data to include the name as well as the customer ID. Well, do that on the fly. Have your enrichment data source called from this Lambda function that's looking at the, so now we've got our raw data coming in, which represents something like a customer, and it's unstructured. So my data transformation function takes the unstructured data, converts it to JSON, takes the customer ID, calls out to my enrichment data source, gets the customer name, and now creates that enriched, structured JSON record, and then passes it back to Firehose. And Firehose will now persist that final record into the destination. And in this case, I'm showing S3, but it could be something like Elasticsearch as well. So now you don't have a back-end enrichment or transformation job. It's all being done in real time as the data is produced. A couple of other ones. So aggregate upon arrival. So continuously write your raw data to persistent store. So basically, one of the nice things about using something like Kinesis Analytics is that it's just a parallel path to something like Kinesis Streams or Kinesis Firehose. So if you're writing your raw streaming data into Firehose, you can also save your raw data into S3. Because in a lot of cases, you want to collect all that data, and you just want to store the value, the original values that were created, but you still want to do some amount of aggregation on it in real time. So the top path here shows our data being passed to Firehose. Firehose is going to store the raw data in S3, unaggregated, just the raw text. But then in parallel, I'm going to have Kinesis Analytics do an aggregation on that data using the business logic that you would write in your SQL code. And then it's going to dump that aggregated data into a data store. And it depends what your end goal here is, but a very typical pattern that we see is a lot of customers stream data into Firehose, persist the raw data into S3, but they want to drive a real-time dashboard off of the data that's being created. So they'll create a Kinesis Analytics application to do like 1-hour roll-ups and then dump the 1-hour aggregate values into something like DynamoDB, and then build a dashboard on top of the Dynamo table, as opposed to building a dashboard off of S3 or off of the data warehouse where they have to run these roll-up jobs later. So with the aggregations being done in real time, that dashboard is updated as soon as the 1 hour is up. So if my business person is looking for some information about the noon to 1 hour period, they will get that information at 1:01 p.m., which is pretty powerful. So with that, I'll hand it over to Brandon, who's going to talk about how they took a lot of these concepts and implemented it in an actual example.
I don't hear it either. There it is. All right. Thanks, Alan. Hey, everyone. So I'm Brandon Smith. I am a software engineer, and I've been at Amazon over 12 years now. I started out in Seattle, worked in the Kindle group for about 8 years. I worked on the original Kindle and on several different projects in the Kindle group. Then I had the opportunity to go work in Amsterdam, and so I transferred out there for a couple years and worked in our office out there in the AWS Workmail team, so I helped build and launch that service. And then I moved to Austin, Texas, where I'm based now, and I work in the last mile delivery department of Amazon. And we're basically responsible for getting all the packages that you guys order from our warehouses to your front door steps. And so for the last couple of years, I've been working on a project called Amazon Flex. And so what is Amazon Flex? So from the screenshot up here on the right, you can see that it's a mobile app for Android and iOS that drivers use to deliver packages to people's houses. How many of you have heard of this thing, Amazon Flex, before? Okay, a few people, yeah. So we have this crowdsourced model that's launched in over 30 cities around the US. And think of it as similar to one of the other gig economy apps, but for Amazon packages, right? So Amazon Flex, this app allows delivery partners who are independent contractors to work as little or as much as they want and control their own schedule. Delivery partners sign up through the app, they onboard themselves, they go through a background check. When the background check clears, then they're ready to deliver. And then the app kind of walks them through all the Amazon delivery processes that they need to follow. It lets them set up their schedule, it suggests turn-by-turn navigation, and shows them their earnings that they have in the app. We also have a sort of second set of users, which are for Amazon Logistics. And these are delivery service providers that are companies that deliver packages worldwide for Amazon. So the app is used to make deliveries around the world for several Amazon businesses. So it delivers standard Amazon.com orders, delivers Prime Now orders, delivers Amazon Fresh, restaurants, and grocery store orders. It's currently used to deliver millions of packages per year all over the world. So as you can imagine, the app has a pretty complex set of delivery workflows to support all the various pickup and routing, scanning packages, all the delivery actions, as well as the offline features like the ability to, for delivery partners to find their scheduled blocks of work which are essentially correspond to different route lengths, so anywhere from 2 to 4 hours typically. So let's talk about the problem at a high level of what we were trying to solve here. What we want to do, similar to what Alan was talking about, right, is to ingest, transform, and load, right? So we wanted to collect, process, and store telemetry data from the Amazon Flex app while it's out there being used in the field to make deliveries. And so what is telemetry data? Telemetry data, the word telemetry comes from the Greek roots meaning remote and measurement. So think of it as any data that you want to remotely measure and collect out from your app out in the field. So this includes things like metrics that we want to see that are happening in the app, crashes when those happen, log data, sensor data, clickstream data, so you can kind of click or see what the user is doing as they're using the app, and that kind of stuff. So for the Amazon Flex app, what that means is we collect things like GPS data, coordinates, and metrics on how the app is being used. We collect events for when the user does things like when they log in, for example, to use the app, when they scan a package, and when a package is delivered. And so to give you a sense of the scale, we kind of talked about the streams earlier. We currently collect and process millions and millions of events per day. And in our Kinesis stream that Alan mentioned before, we currently process anywhere from 5 to 20 megabytes of data per second coming into those streams. And it kind of depends on the time of day as it peaks up and down. And so what is the goal? What's the goal that we had here? Basically, it's to understand what's happening out in the field. We want to make sure that our app is performing at its full potential and very efficiently, so that if it is, right, it can save millions of dollars over the course of a year. And more importantly, improve and make the delivery experience better for both the delivery providers that are using the app and for the end customers that are getting packages delivered to their houses. And so what we really want to do is to collect and analyze all this telemetry data so we can optimize the app's performance and the delivery workflows. So we can focus our time on improving how the app is working, how performant the app is, and how intuitive and easy those delivery workflows are for the users. So for example, some of the ways that we've been able to improve the app performance include optimizing the login time, optimizing the different network calls that the app makes, and improving our routing algorithms based on the actual route execution that has happened. Okay, so next I'm going to walk through some use cases. These are just some use cases that we had that we wanted to solve. They're probably similar to some of the use cases that you may want to solve with your applications. You don't have to remember these use cases. I'm just kind of giving them as examples to walk through as examples. And then later in the talk, I'll go over the actual architecture and the solution that we came up with and how we solved some of these use cases. So the first one is to collect real-time metrics so that we can build alarms. Right? This is probably the most important thing when you're building an application, is to alarm so you know when something is not working right. Ideally, we want to know within minutes if there are any delivery problems, either worldwide or isolated into a city or neighborhood that we're in. So for example, if the delivery count drops below our expected thresholds, we want to trigger an alarm so we know about that and we can look into it. Or perhaps we'll schedule more drivers to pick up the slack and, if there's a surge in demand. Or maybe there's a bug that we've discovered that we know we need immediate patching. And so alarming, as you can see, is very important. Really, this use case is all about monitoring and alarming when something goes wrong. The second use case is for troubleshooting. And so having alarms and being notified of the problem is the first step. The next step is to be able to troubleshoot what's happening out in the field when there is a problem that's identified. So in this case, we wanted to be able to do real-time log and crash analysis. We consider logs and crashes telemetry data because, as I mentioned before, it's all remote data that's being collected or that's happening out in the field. So it falls under this kind of telemetry bucket. So what we do is we want to do is publish all these logs to CloudWatch logs in AWS, where you can filter and search and look through all that data in real time. And as a developer that's in the on-call rotation, this is really kind of an essential tool, right? as you guys probably know, for being able to remotely figure out and diagnose what's happening out there in the field. The third use case is another pretty common one. It's to have reporting dashboards. So normally in the batch processing that Alan mentioned before, you can write SQL, you can generate reports, you can create visualizations from that data. But what we really want is real-time dashboards instead of sort of daily or hourly batch reports. So clearly, to achieve this, we need to go from daily batch processing to real-time metrics dashboards. We wanted to have dashboards to monitor various things, including having health dashboards for operations managers that are seeing what's happening in a warehouse or delivery station, having crash report dashboards, and having deployment status dashboards. This data is all aggregated and anonymized, of course, and so we're kind of looking for the general trends in these reports and these dashboards. The next use case is for releases, for deploying software updates to the app. Deploying mobile software app updates can be tricky, as some of you may know, when you have to consider that it's worldwide. There's various configuration options. The backend services could be changing at the same time underneath. And so it's really important to be able to monitor and see the status of your deployments as they're getting rolled out around the world. And so when we deploy new app versions, we want to monitor these, the status in real time. And we wanted to be able to release code smoothly and confidently. So for example, it's valuable to see real-time metrics and visualizations in dashboards for the different release candidates that are going out, and to sort of smaller subsets of users and smaller groups that we're deploying the changes to before we deploy it out to everyone around the world. Because obviously, our app is being used to make millions and millions of deliveries, right? The next use case is for data sharing. Right? So we want to be able to share our data with sister teams in the Amazon last mile delivery group. An important key here is that at Amazon particularly, I'm sure a lot of other companies as well, information security is a top priority, right? Because our customer trust is our top priority. So, one thing we do from the beginning is we want to follow the standard security and encryption best practices, and only grant the encryption key access and permissions to that on a need-to-know basis. So what we want to do here is we want our new telemetry data to go into S3 so that sister teams can subscribe to that data and get the SNS notifications and consume that data in near real time. So our customers then want to take that data and join it with their own data sets. So they may have their own backend services or their own backend data sets, right, where they might want to combine the data with the telemetry data from the client, from the applications, and then kind of combine that and analyze it all in one place. And so we really kind of want to create these data lake, right, these data lakes of data so that other teams can catalog and find and discover data that's useful for them and interesting to them for their business use case. I'm sure I think I saw a few other talks on this concept of data catalog and data lakes that you can check out later this week for more on that. And then the final use case extends a little bit upon the previous one. And so what this one is to be able to do deeper analytics and use some of the machine learning type of tools. So looking at both the stream of new data and the historical data, we want to be able to build machine learning models on the data, create predictions, and detect anomalies. We also want to be able to support a variety of frameworks, right, that for processing and analyzing the data. So we want to be able to support Hadoop. We want to be able to support Spark and Storm, these type of machine learning frameworks and different frameworks that the machine learning scientists and the business intelligence engineers that they typically use and that they're familiar with and the tools that they like so that they can easily access the data and they can easily analyze it on their own. And so all this data, again, with the security in mind, should be anonymized and aggregated at the appropriate level, so we need to be able to solve for that. To meet both the business use case so that the data is valuable for analysis, but also has the right level of information security. And so some of the questions that you can imagine that our business wants to answer includes modeling how increased surge prices might affect driver demand, predicting how the supply of drivers might be needed, to work on a given day, and doing analysis on A/B testing results for different features that we're rolling out. Okay, cool. So now we're going to kind of transition into, from the problem and some of the use cases that we wanted to solve, into actually how we built this for the Amazon Flex team. So as Alan mentioned, one of the best practices, the first thing to mention is that we tried to follow an Agile mindset. We wanted to build things iteratively. So we started with an initial batch processing system as kind of initial version, proof of concept version, and then we evolved it over several iterations to get into a stream-based system. And so we'll walk through that. We'll walk through that next. This can definitely be tricky when you have a live production system. I'm not going to get into the details of how to do that or how to change the car tire while you're driving. So if you're interested in this, we've learned some stuff in this area. So feel free to find me afterwards, and we can talk a little bit more. So for the rest of the talk, we'll go over the high-level system design, how we implemented this, and how we kind of progressed incrementally from our batch-based system into a real-time streaming system. Okay, so the first iteration was to use existing systems that existed within Amazon. And so this was the fastest way for us to get some data and to see what's happening in the app, right? So we instrumented the app in the code for both iOS and Android to collect metrics, send those metrics to existing backend systems. I just drew a cloud here to give that concept. And then we built ETL jobs to load the data into this big Oracle data warehouse. And from there, we could query it, we could build reports, we can a very like batch-based system, right? And to analyze what's happening. And so this initial version was fine. It was suboptimal, but it kind of got the job done initially. But there were some problems with it, right? So some of the main problems were, one is a batch process, right? And so doing reports had a 24-hour delay. Second, it had a very fixed and inflexible database schema. Couldn't really change that very easily. And then third, analysis was both slow and difficult because you had to write SQL, and that was really the only way to access the data. All right, the second iteration was to use AWS. And so what we decided to do was to use the Amazon Mobile Analytics, or AMA, service that AWS had. To do this, we just had to use the AWS SDK to instrument the app to collect events. And associated with those events, when things happened in the app, when the driver delivered a package, or when they scanned a package, or things like that, associated with each of those events was different attributes. You had context around what happened with that event, and metrics, so different actual timing data or count data, that kind of stuff. And so, yeah, as I said before, like we instrumented when they logged in, when they scanned a package, that kind of stuff. And so the data would be sent in through the app, through Amazon Mobile Analytics, and then part of Amazon Mobile Analytics was they gave you a CloudFormation template that ran in your own AWS account and had a Python script associated with it that would load data from AMA into your Redshift cluster. And so for those that don't know what CloudFormation is, real quick, it's a way to define, it's a template language, a way to define your AWS resources that get deployed into your AWS account. And so, yeah, that set up this whole CloudFormation ETL system that loaded data into Redshift. In the future, we used AWS Pinpoint, which kind of got merged in with AMA, and we'll kind of talk about that a little bit later. And so now, this ETL system was now run hourly, so in worst case, it was a 2-hour delay. But it was still a very fixed, inflexible database schema, and analysis was still slow and difficult with SQL. So with the third iteration, we implemented an automated system to update the database schema in Redshift. This is important because it makes adding new events easier. And so what we did is we defined the schema configuration file. It was in JSON, and it did two things. One is it automatically updated the schema in Redshift, so when we added a new event or we added a new column of metrics data that we wanted to collect or telemetry data that we wanted to collect, there was an automated job that would automatically update the Redshift schema. And then the second thing it did is we generated both Java code for Android and Objective-C code for iOS to generate enumerations of possible values that we could collect in the app, so that when you're instrumenting your data in the app for collection, those values would be sort of defined in code for you. So you could just kind of reuse those, and they would match what shows up in the database in Redshift. And so if you used AWS Glue before, I think this is one of the fairly new AWS services. This is a little bit different than what they do for keeping their data schemas up to date. What we've done is we've essentially built a configuration-driven system where we define this config in JSON, and it generates the code and automatically updates the schema in Redshift. We only ever do additive changes, of course. So this conforms to the open-close principle in OO design, right? And so we never modify or delete any existing data, which makes sense because if it's telemetry data, it's historical data, and so really it's immutable, right? So you don't really expect it to change. And so this system would work well with AWS Glue because Glue uses what's called a crawler to discover your data. And so it crawls over your schema in Redshift or whatever other data store you're using, and it updates its schema in the Glue data catalog. And so once our automated system here for doing the schema config updates, once it updates our Redshift schema, then Glue's crawler would see that change and update the data catalog. So this would play well with that. But so long story short, we automated the database schema updates in Redshift so that we're always matching what data is being collected from the app. And so we still have this 2-hour batch process, but now our schema automatically updates, so that makes it a little bit easier for adding new telemetry data types. You just have to, as a developer, you just have to edit the schema configuration file, and now it defines for you the schema that's in Redshift automatically and the schema of available telemetry data that you want to collect from your app. So that makes it simple. Okay, so now, iteration 4, the moment you've all been waiting for is to use streams, right? And so we introduced streams here. We still use Amazon Mobile Analytics to collect the data, but as I mentioned, it's now part of Pinpoint. It got rolled into that service, and Pinpoint supports loading your data into Kinesis streams or Kinesis Firehose. So instead of using this CloudFormation stack that we had before, Pinpoint just publishes the data into a Kinesis stream, and then from there, we can load it into a Kinesis Firehose, which loads it into Redshift. And so what we did is we wrote a Lambda that filters out the events that don't conform to our schema. So that JSON schema config that defines the possible values, if you don't follow that, if one of the developers does not use that, and they send an event that's sort of unknown, then we filter it out in the Lambda there that's between the Kinesis stream and the Kinesis Firehose as sort of an unknown data type or unknown event, right? And so that's one nice thing to make sure your data is always clean. But then the data from there gets loaded into Kinesis Firehose, and Firehose has what are called delivery streams. And from there, you can configure those delivery streams to publish data into either Redshift and S3 or Redshift and Elasticsearch or S3 and Elasticsearch, sorry. So now, rather than an hourly batch job, it comes in through the stream, goes to the Firehose, into S3. And it took 4 iterations, but now we got into a streaming system. The other improvement that we made as part of this was we also implemented data retention logic. And so what we did is we created, in our Redshift, we created monthly tables of data. And so we could configure easily how many months worth of data we wanted to keep and drop the tables that were older than X months. And all the data would always be kept in S3 forever, but then that keeps our Redshift costs lower because we can control exactly how much data we want to keep in there. So now we have a streaming process with a delay of just a couple minutes to get through from the app, through MA, through the Kinesis stream, through the Firehose, and into Redshift and S3. Yeah, so we did it. So we're not done yet, right? We still have this data that only goes to Redshift and S3, and it's kind of difficult to analyze, right, with SQL. And so here we go. In the final iteration, in our current one, we introduced generic message types. And so what we wanted to do here is we wanted to publish data according to, you may have seen this pattern according to data temperature, right? So you have like warm, cold, and hot data. And so all the cold data for all time goes to S3. Redshift keeps the warm data, which may be the last few months. And then Elasticsearch just keeps the hot data, which is maybe the last month or the last couple weeks worth of data. And so at a high level, it looks like this. The data comes in, we collect it, we ingest it from the app, the Kinesis Firehose gets it, transforms it, and then it loads it into the various data stores. And so let's go into a little bit of details of how we did this and how we simplified this and optimized this system. So first, you probably noticed on the previous slide that there were 2 Lambda functions. There was one that filtered out events before it went into off of the Kinesis stream, and then there was the transform Lambda. And so we combined those into one to simplify that. And so that allowed us to get rid of the Kinesis stream entirely, right? So we utilized the Kinesis Firehose transformation Lambda here and cut out the previous Lambda with the previous Kinesis stream. We also cut out AMA, right? So at this point, there was really no, we didn't need to use that. And so what we did is we went directly from the app straight to the Kinesis Firehose. And so now we control that code. We control that code rather than using the AWS SDK to send data through AMA, we can now use the AWS SDK to send data to Kinesis Firehose, and so we can control the schema of data. And so what we were able to do here is introduce generic message types. And so we can define those message types for the various types of data that we want to collect, telemetry data we want to collect. And so what we did is we used protocol buffers to do that. And so we have these protocol buffers to define the structure of the data. And if you haven't used protocol buffers before, think of it as an interface description language, kind of like an optimized version of XML. And so what it does is it generates source code in various languages, so in Java and Objective-C for us. And then we use it in multiple places. So I'll show it up out here, right? So we use it in the app from the generated code. We use it in the transformation Lambda when processing the data. We use those protocol buffers for updating the Redshift schema when new telemetry data types show up. And then any consumers that want to consume the data can use those protocol buffers to deserialize and consume out the data, right? And so now the system allows us to collect, process, and store any arbitrary type of telemetry data, including metrics, logs, crashes, sensor data, clickstream data, anything like that, anything that we talked about before with telemetry data. And now we're no longer tied to just Redshift either. We configured our Kinesis Firehose delivery stream to publish to Redshift and S3 here. And then we also had our transformation Lambda publish data into a second Kinesis Firehose to load it into Elasticsearch. There's also once the data is in S3, there's also the ability to subscribe to that data through SNS topics, right? So other teams can write their own consumer Lambdas and subscribe to that data and process it in real time. Or they can extract it out of S3, load it into their own Redshifts, join it with their data. And so this kind of opens up multiple ways to consume the data. Once it's in Elasticsearch, it's easy to do dashboards. You can use something like Kibana or other visualization tools to visualize that data in real time. OK, so now to summarize for this final iteration, right, we have now a streaming process with just a few seconds delay from the app into the data stores in the backend. We have an auto-updating database schema, and we have generic message types so that we can support any types of data that we want very easily. And now analysis, we can still do SQL, but it's now a little bit more flexible because now we can process these message payloads, and you can kind of process them as you like, as you want to consume them. If you want to write custom code in your own Lambda, you can. So that's an option. OK, so now just to get a sense, I know it's a little bit hard to follow with these diagrams. I'm going to walk through the data flow really quickly to give you an idea of how data flows through the system. So first, let's start in the app. The app is collected. We use this protocol buffer to generate source code, and then you instrument the app for Android and iOS to send the telemetry data that you want to send. The data is serialized by the protocol buffer and loaded into a Kinesis Firehose, sent to Kinesis Firehose. We kind of batch the data into 5 kilobyte chunks to kind of take advantage of the 5 kilobyte pricing that Kinesis Firehose has and kind of optimize our costs there. Firehose buffers up the data in 5 megabyte chunks. So we receive 5 megabytes pretty quickly. And it's typically under a second. And so now the data is there in Kinesis Firehose. Then the transformation Lambda gets called. And it converts those 5 megabyte chunk files into JSON and puts them into S3. And so now they're in S3. Then Firehose issues a Redshift copy command to load the data into, from that transform file into our Redshift instance. And then the data transformation lambda also does one thing. It copies the data into a second Kinesis Firehose, which is configured to publish the data into Elasticsearch. So now we're at this point where our telemetry data is coming in. It's getting replicated within seconds to the 3 different data sources, S3, Redshift, and Elasticsearch. And now from here, we have multiple consumers of the data. We have the data joining use case and the data lake use case, right, where other teams want to join the telemetry client-side application data with their back-end service data. And so they can do that. They can take the data out of S3 and load it, combine it with their data, load it into their own Redshifts, and do joins there. We also have other teams who want to consume the data in near real time, so they can subscribe to the SNS events when stuff gets loaded into S3, and they can write their own consumer lambdas to use the protocol buffers, deserialize the data, and now they just have the data. They can write code, process that data. We still have Redshift, so we can still write SQL and generate reports that way. And now, since it's an Elasticsearch, we can use Kibana and other dashboards, right, and view things in real time. So that's kind of how data flows through the system. Hopefully that's clear enough and easy enough to follow. One common question that we get is, why use Kinesis Firehose as opposed to a Kinesis stream, right? So the biggest benefit, I think Alan mentioned it as well earlier, is that Kinesis Firehose is a fully managed service. It's sort of one level higher up than just a Kinesis stream. And so this data transformation lambda gives you flexibility, right? We had sort of that duplicated two lambdas that were doing similar things, and we kind of combine that all in one place since you have this convenient transformation lambda in the Firehose that lets you process and transform your data so that it's easy to load into different data sources. You can certainly write that code in your own Lambda function, but Firehose handles that for you and just makes that kind of data binding between things a lot easier. So yeah, future improvements. Some ideas that we've talked about that we can do in the future to make things better. Alan mentioned Kinesis Analytics. We're not using that yet. We can. We want to use that next. That will allow us to query and extract some of the data in real time. The other idea is to use something like AWS Athena or Redshift Spectrum to query data. That's in S3. Oops. And then finally, we can use something like some of the AWS AI services to do deeper analysis. So, for example, we could use some of the frameworks like TensorFlow or MXNet or Spark or Amazon EMR and process the data and try to extract more deeper analysis out of it, more deeper data analytics. But really the nice thing is since we used AWS for all this, we have a system that's flexible. It enables us to use any number of other frameworks that we can plug into the system and we can use to process our data. Okay, so to summarize, did we solve all our use cases? Yeah, we did. So, first we have real-time metrics and alarming. We have dashboards. We have the real-time logs and crash data that we can use to troubleshoot issues when they happen. We can monitor new releases with our app dashboards. And now we publish the data to S3 so that we can share data with our teams and sister teams and enable deeper analytics use cases. And so, to kind of wrap up and give you a sense of the business impact that's possible that we had with the Amazon Flex delivery business, one of the pieces of telemetry data that we measured is the negative impact that it made on delivery partners when the app crashes while making a delivery. And so when the app crashes while making a delivery, what we did is we record a timestamp when the crash happens. And then we calculate the difference between when that crash happened and when the user got back to the screen that they were on before the crash. So we're basically measuring the time lost due to crashes, right? And so over the past 3 months, we looked at the metrics, we looked at the real-time logs, we looked at the crash data, and we were able to reduce the number of app crashes and to the point where we were able to save about half a second per delivery. Right? So theoretically, for 1 million deliveries, that would be 500,000 seconds, which is roughly 160 hours, which is roughly 4 40-hour work weeks, which is roughly a month work month of time, right? That we're saving in frustration for our drivers. So that's a pretty significant thing. Over the course of a year, right? If you add all that up, we're speeding up these deliveries, and we're speeding up delivery time for our customers. That is measured in months or years, right? Which is a significant amount of time savings and making things better for our customers, right? And so without doing this, without collecting all this telemetry data, measuring these improvements would not have really been possible, right? Okay, so what are your takeaways from this talk, just to wrap it up? So first is agility, right? Moving to real-time data means your business can react quicker. Increased flexibility means that you can support and having generic message types that you can put whatever data you want in your streams allows you to handle future use cases easier. Streams allow you to multiplex and share your data, so you have increased shareability with other teams, right? You can put your data S3 and people can consume it through SNS. And then finally, extensibility. Processing streams allows you to write to multiple systems and enables other tools and other frameworks to be able to work on top of that data, right? And so really, by moving from batch SQL-based processing to real-time streams, we can extract more business value from our data, and we can improve our customer experience for our customers. So that's it. Thank you.